To determine the contributions of different sections of the cerebral cortex to neural network interactions and cerebral function, some method of deactivation is necessary. Using an animal model is one way to study cerebral deactivations. When a section of cortex is deactivated, a change in behavior can be studied to determine the contribution of that section to normal function and behavior. Lesioning the brain has been a common method of deactivation, but there are drawbacks. The exact location and extent of lesioning can only be defined post-mortem, so if the lesion is not in the intended location or has deactivated more of the cerebrum than desired, the time and resources have already been spent on the experiment while obtaining less than ideal results. Also, lesions permanently deactivate the section due to damage or removal of the neural tissue. Since the tissue cannot be reactivated, control measures that can be directly compared to the deactivation-induced effects cannot be obtained. Comparisons between animals, which will have inherent differences, must be made, so internal double dissociations are not possible. Another major drawback in using the lesioning technique is that because the brain is plastic, while animals are recovering from the lesion surgery, the cerebral cortex is able to modify the neural networking by activating new connections or strengthening pre-existing ones. This could cause the resulting behavior to appear normal even though part of its brain has been deactivated, and then experimenters would not be able to tell the contribution of the deactivated section. Cryoloops are devices that cool the cerebral cortex to deactivate it. Cryoloops are made of metal tubing that has been shaped to fit into sulci or on the gyri of the cerebral section of interest. Cooled methanol flows through the tubing, which is secured using a threaded post attached to a thermocouple connector. The post, connector, and Teflon tubing are sealed using dental acrylic. The tubing temperature is measured by a microthermocouple. After implantation, when the animal is not participating in the experiment, a protective cap is placed over the inflow and outflow tubes. After implantation of a cryoloop and during experimentation, the cryoloop is hooked up to Teflon tubing that enters a dry ice bath to cool the methanol. The thermocouple connector is connected to a switch box and a thermometer so cryoloop temperature can be monitored. Using cryoloops overcomes many of the drawbacks of using lesions to deactivate the cortex. Because the loops can be designed to fit with a certain section of the cortex, specifically selected regions of tissue can be reversibly deactivated in a controlled and reproducible way. Control and experimental data can be gathered with the same animal since the deactivation is reversible, thus reducing the number of animals needed and increasing sensitivity by enabling double dissociations. It only takes minutes for the tissue to cool or to revert to normal conditions when the flow of cooled methanol is terminated, so no possibility of neural compensation affecting behavior exists. Also, large amounts of data can be gathered with the same animal. These advantages hold even when deactivations are repeated over long periods of time, from months to years, with no evidence of attenuation. In 2006, Drs. Lumber and Malhotra published a paper entitled Sound Localization During Homotopic and Heterotopic Bilateral Cooling Deactivation of Primary and Non-Primary Auditory Cortical Areas in the Cat. To determine what parts of the auditory cortex contribute to sound localization, these investigators used cryoloops to deactivate each of the 13 known regions of acoustically responsive cortex of the cat. 4 tonotopic areas and 6 non-tonotopic areas were of interest for deactivation. 21 cats learned to make an orienting response by moving their heads and approaching a 100 millisecond broadband noise stimulus emitted from a central speaker or one of 12 peripheral speakers located at 15-degree intervals from left 90 degrees to right 90 degrees along the horizontal plane, after attending to a central visual stimulus generated by a red LED. After the cats had reached at least 80% accuracy in identifying the location of the sound stimulus, each was implanted with 1 or 2 bilateral pairs of cryoloops over different sections so that at least 3 cats had a cryoloop for each of the 10 sections of interest. After cryoloop implantation, experiments began. Cats performed orienting responses while baseline data was gathered when the cryoloops were off. Then the left hemisphere cryoloops were turned on so that the loops reached a temperature of 3 degrees Celsius plus or minus 1, and task performance was recorded. While the left prior loops were on, right hemisphere prior loops were also activated so that both prior loops were on while the cats oriented themselves toward the sound stimuli. After this, the left prior loops were turned off while the right ones remained on. Then the right prior loops were turned off so that both were off, so the brain could equilibrate back to 37 degrees Celsius and orienting responses could be measured at baseline after recovering from cooling. This cycle was repeated several times for each cat, but also in reverse order of baseline, right, both, left, baseline. Of the 10 sections that were deactivated, only deactivation of 3 sections, the A1DZ, TAF, and AES sections, were found to have an effect on sound localization. Unilateral deactivation of any one of these sections resulted in a contralateral impairment in sound localization. Bilateral deactivation of these sections resulted in a 180-degree deficit, although cats were able to orient to the hemifield where the sound occurred above chance. To clarify, at baseline, cats were able to correctly identify the sound localization approximately 90% of the time. When one of these sections was deactivated, let's say on the right side, the cat could identify the sounds that occurred on the right side with 90% accuracy, while any sound that occurred on the left side could only be identified with approximately 10% accuracy. If one of the auditory cortex sections was deactivated on both sides, the cat could identify the location of the sound with approximately 10% accuracy, which is above chance, or 7.7%. After the experiments, the neural tissue was examined to determine if any damage had been caused during cryo loop implantation and cooling deactivation, and no damage was found.